Let's take a look at our first integration strategy called substitution. Now, while most Calc 1 teachers do cover this section at the end of Calculus 1, some of you may not have seen this, and this is our first official integration technique beyond the basics. It's our first official section to start off Calc 2. So this method, this technique for integrating is called substitution, and it is taking a derivative technique, the chain rule, for when we take the derivative of a composition of functions, which I have written here. When we have a composition of functions, we take the derivative f of g of x, we take the derivative of the outer function evaluated at the inner function, and then we multiply by the derivative of the inner function. So I've got several different compositions down here as examples, but let's just apply that chain rule to one of them, just so we can do a quick little recall of our chain rule from Calc 1. So taking a derivative, not taking an integral, but we're going to take a derivative, see how this chain rule works so that we can go the opposite direction and integrate using a process called substitution. So when we take a derivative of a composition, we identify the inner function. So in this case, the inner function, and we call it u. The inner function is 3x squared minus 7x plus 13, and the outer function is what it got composed into. So the outer function in this case is that logarithm. So the outer function in this case, we call it y, and it's the natural log of u. So that's, just when we're taking derivatives, we identify those. Once we've spent a lot of time working with the chain rule, we don't write a lot of this, but we identify it in our minds, in our heads, in our thoughts, as we're going through and taking the derivative. So when we take the derivative, we have to take the derivative of the outer function first. So when I'm taking the derivative of a composition, I know I had it on the previous screen, but let's just write it here. When I'm taking the derivative of a composition, I take the derivative of the outer function first, evaluated at the inner function, times the derivative of the inner function. That can also be written as f prime of u times du dx, if we want to write it like that. Okay, so we take the derivative of the outer function, the logarithm, so we get 1 over what the inner function is, which is 3x squared minus 7x plus 13, and then I have to multiply by the derivative of that inner function, so I get 6x minus 7. So the derivative, applying the chain rule, is 6x minus 7 over 3x squared minus 7x plus 13. So this section is about how, pretend like I hadn't just taken that derivative, how would I find the integral of something that looks like that? 6 minus 7, I keep wanting to say 7x, 6x minus 7 over 3x squared minus 7x plus 13. If I'd come across this question, how would I integrate that? And that's where we come up with our first integration technique beyond just the basic integrals, basic integration formulas. And so how would I do that? And what we do is we go through a process called substitution, where from this integral, we figure out what would have been that inner function. And we do what's called a substitution. We make a substitution so that the integral will become in terms of u. So let's take a look at one of those. Okay, so steps to actually applying this substitution rule. So the first thing that we're going to do is we're going to actually identify a u. Now, like I said, we want to find that inner function, right? We're trying to undo a derivative that was the derivative of a composition where we applied the chain rule. So in order to do that, we have to figure out what was that inner function. So we're looking for that inner function. Now, there is some other verbiage I put in here. Another thing to think of is you can look for a function and something that resembles its derivative. That is something else that we can think of. But the first thing we do is we identify that u. So when we come to an integral, let's take a look at this problem that I have written over here. When I come to an integral, and I think maybe substitution is a valid technique here. And here I'm looking at this function and I'm seeing this function, 2x squared minus 5x plus 1, and it's inside of a power. And so that looks like a good candidate for my u. I also notice, so if we say u equals 2x squared minus 5x plus 1, I also notice this other function that does resemble the derivative of u. Now that might be harder to see on first glance without taking the derivative, so let's go ahead and take the derivative. So we're going to take the derivative, so we find du dx, take the derivative, and that's going to be equal to 4x minus 5, and then we separate the differential, so we multiply both sides by dx, and we find that du equals 4x minus 5 dx. So just a minute ago I said this is my inner function, and this resembles something like my derivative of my inner function of my u, which might have been a little bit harder to see without actually having taken the derivative. But notice now that we've taken the derivative of 2x squared minus 5x plus 1 is 4x minus 5. It's a little linear function. And notice this isn't exactly the derivative, but it does resemble the derivative. It's really close. In fact, it only differs by a 2. And so now what we're going to do is we're going to do some manipulation. We're going to manipulate the integral or the du so that we can make some substitutions, so that we can turn this integral into an integral in terms of u. So right here, this is my u. I already have my u. I can make that substitution. This right here is almost du, but it's 8x minus 10 dx instead of 4x minus 5. So I look at that and I think there's actually two things you could do. You could either manipulate within the integral itself, or you can manipulate your du. And you can do that algebraically or with constants. We do have to be a little bit careful with divisions by zeros and things of that nature with domains. But in this case, I notice if I multiply both sides of my du equation, I find that 2 du is actually equal to 8x minus 10. And now I can make two direct substitutions. So notice over here my work in red where I'm manipulating the u in order to make the substitutions. I do have some steps in there where I manipulated it and played around with that, but the two that I have highlighted are what I'm going to use to make those substitutions. So I'm replacing 2x squared minus 5x plus 1 with u, and so u to the 7th, and then the 8x minus 10 dx is exactly equal to 2 du. Now that little dot I wrote right there is a multiplication, because there is a multiplication right here and I made a substitution. And that constant, we can always pull constants out of the integral. So that's just 2 times the integral of u to the 7th du. And this is the goal of substitution. We now have an integral in terms of u. And it's completely in terms of u, and we're being asked to integrate with, notice the differential, with respect to u. So this is an integral in terms of u. It's an indefinite integral. I can now find the integral, find the antiderivative. So I have 2u to the 8th over 8. I will have an integration constant plus c. So that is 1/4 u to the 8th plus c. And the very last step, and I'll go back to my steps in just a second, but the very last step here is to then back substitute your u back in. So that's 1/4 2x squared minus 5x plus 1 to the 8th plus c, and that is my answer. Now remember, the goal here, the reason that we do this, that we make these substitutions, is so that I can actually get to I can make the substitution and I can see one of my basic integrals, so I can apply my basic integration techniques in order to integrate. So I do a substitution, I look for the u, the inner function, I take the derivative, make the substitutions for both u and for du. So I get an integral in terms of just u. I integrate with respect to u, and then in the end, I substitute u back in. And those are the steps here. I'll erase some of my highlights. But those are the steps that you want to go through right here. So steps for applying the substitution rule. Determine your u, compute your du, take the derivative of u, which is du dx, and then multiply both sides by dx. Manipulate the integral, or you can manipulate the du, make the substitutions, integrate with respect to u, and then simplify and back substitute. So the solution is in terms of u. So I do have one more set of steps right here with another example. I will zoom out on that. before we get into any more examples. I'll zoom out on that. And I think we'll save the examples, the next set of examples for the next video. But that is the basic steps for U substitution. So I have an example typed out here with a little bit more detail and a little more explanation if you wanted to screenshot that or pause it and look through that example. But again, when we're applying the substitution, we're essentially undoing a chain rule. So in order to do that, what we do is we look for that inner function, call it U, take the derivative du dx, and then isolate du. And then we have to make some substitutions. So that's where we have to get sometimes a little bit creative. We make the substitutions till we have an integral in terms of just u, and then integrate in terms of u, find the antiderivative of the integral, and then back substitute. Okay, we'll do more examples, lots more examples on the next couple of videos.